Hello everyone, I'm Lucian, and today I'll be talking about how we can exploit error correction codes. Basically, how we can still run a Rowhammer attack on ECC memory. Actually, the story is about how I spent my past, let's say, 2 years, and what is the thing with the syringe needles, and what is my life. I'm not sure if I had no life, but anyways, the internet is right most of the times. So Rowhammer, we all know that Rowhammer causes bits to flip. That's like the canonical example that we can use to trigger these bit flips. We also know that there are lots of exploits already written, and people show how we can escalate privileges or how we can escape sandboxes. Again, we can also compromise confidentiality. And also, the Rowhammer attack was shown to work on desktop computers, on phones, and even we could trigger bit flips in GPUs. And we can do so even from over the network. So this is all previous work. However, every previous work so far was working on non-server memory. So the question is, what is so special about server memory? And this is where ECCploit comes into play. So ECCploit is a Rowhammer exploit that will work on server memory. Server memory has a special capability most of the times, and that is it can correct some of the bit flips. It does so by using an extra chip that stores this control or redundant bits. So ECCploit aims this type of memory. This is the overview of my talk. I'll try to introduce some challenges for pulling the Rowhammer attack on ECC memory. I also argue why single bit flips are still important for ECC memory and how we can build upon these single bit flips to launch the final attack. And lastly, I'm going to show how we reverse engineer some ECC functions that are implemented in hardware. And of course, I have to talk about the results. Now, as I said, ECC just corrects some of the bit flips, right? But so what makes then the exploitation of ECC memory so difficult in practice? We just need more bit flips. That should be the strategy, right? Well, it turns out that more bit flips makes the life harder for us, and also it could be dangerous to get too many bit flips at some point. In short, the odds are against us. So for example, it's very easy to get one bit to flip. There are so many bits that are flipping. There are so many 1 bits that are flipping, but it's very difficult to get, let's say, more or 3 bits that flip. So this is the probability of encountering these cases. So let's see what happens when 1 bit is flipped. So when one bit changes in memory, any ECC function out there will be able to correct it, right? Because it stands for error correction code, and at least it should do something for at least 1 bit. If 2 bits are flipped, then this could be a potential uncorrectable error. And potentially the machine, if it detects this potentially uncorrectable error, then the machine would crash, or at least the process that causes the uncorrectable error will have to crash. So a countermeasure has to be taken by the host. If more bits are flipping, then this error it could be a potentially uncorrectable one and potentially undetectable. So we have a chance there to go, let's say, undetected. So I have mentioned the word potentially several times in this slide, and the reason for doing so is that some of these details are very implementation specific. So for example, not all 3 bits that are flipping can be corrected. Some of them are just not detected, right? And this is basically to put it in the Rowhammer context, 1 bit. If we flip 1 bit, then this is kind of useless for Rowhammer. We cannot exploit a bit that was corrected. If 2 bits are flipping, then the machine crash, and the machine will crash. And actually, this is just a denial of service attack. And to date, this is the state of the art. So we kind of know that Rowhammer on ECC memory will cause a denial of service attack. And this is our baseline. So ECCploit comes here in place and upgrades this denial of service attack to a powerful attack. We managed to cause undetectable bitflips. Thus, these are like silent error corruption, silent memory corruption. Right. So this is what ECCploit does. Let's see how it works. Well, the question is how we can get from 1 bitflip to 3 bitflips without causing these crashes. So without having two bitflips. By the way, here I'm using 1, 2, or 3, but in practice, it really depends on how ECC is implemented. And these are some, let's say, some example guarantees that that ECC can give. But I'm going to stick with these numbers now for simplicity. Right. So the question is, how do we get from 1 to 3 bitflips? Well, we devised a strategy which roughly has 2 steps. First, we gather single bitflips, so we gather a set of single bitflips. We can do so by Rowhammering. And then we try to combine or pick some combination from this set of bitflips and see how many of these or which one of them, the combination, will cause a silent corruption. Basically, the ECC function will return the same value for the original data, but also for the corrupted data. So this is, in a nutshell, the attack. Now, let's look at some challenges. So I'll talk about getting these single bitflips. So so we can cause a single. We want to cause just exactly a single bitflip. If we would cause 2, then the machine will crash, and of course the exploit will be detected. The way to do this is to piggyback on the fact that most of the bitflips, they do have a direction of flipping. So let's say if a bit only flips from 1 to 0, and if that bit flip has the 0 as the original value, then the bit wouldn't flip back. So the idea is to mask at the time, or to unmask at the time, a bit that we target. So in that example, we have the 2 aggressor rows, and we have the victim row in between. And we would just want to test if the bit that has the value 0 has a bit flip or not, could flip or not. We do this for the first bit in a row, and then we move on to the other bits in the victim row, and so forth. Right. So right now we have a way to cause exactly 1 bit flip. But anyway, I said that ECC will correct at least 1 bit flip. So the next challenge would be to see how we can observe that our bitflip candidate is actually a bitflip or not. And I think every speaker before me mentioned side channels. Yes, side channels are everywhere, including in the error correction hardware. So you can imagine that when a bitflip is corrected, there's, let's say, a slow path that is taken, and this path has, or an error path in the hardware, and this path will have a performance on the memory axes. So for example, here we have 5 instances of bitflips. The y-axis measures the performance, basically the number of cycles it takes to access the memory, and the x-axis is just an offset inside the row that we test for bitflips. So it's word offset, right? And we can clearly see a distinction between normal execution and some of those peaks. Actually, it turns out that those peaks, we had a way to check where the bitflip happened. Actually, those peaks, they do correspond to a bit being corrected by the hardware. Right. So I talked about how we can get the single bitflips, but let's see how we can combine them to cause these silent corruptions. Again, the goal of this step would be to combine some of the bitflips such that the ECC function will return, let's say, the same value. So if it's the same value as the data not being corrupted, then this will be a silent corruption. And this is what we are looking for. Furthermore, you can think about ECC that it does not correct any bit flips, but actually the bits that are being corrected, they are also depend on their position. So ECC would not correct any bit flips, but let's say it will correct first, second, and third. But then if the bit flips are actually mapped, let's say the first one, and then we have 2 bytes and then another bit flip, this error, maybe it's not corrected. And all of these details are very much implementation specific. In addition, there's not much, this implementation, which is very much tied to hardware, it's not something public. So it's very hard to get some documentation about it. Usually you get some guarantees, like it's a SecDead-like implementation, but not more than that. So as I said, there's not much documentation out there, so what can we do? Our approach was to reverse engineer some ECC implementations that are out there. We started with the observation that if we have access to error correction errors, in the ECC terminology, these are called syndromes, these errors, these intermediate results, are actually revealing information about the ECC implementation. We had 2 approaches here, one based on fault injection, with some needles, and one with a cold boot attack. In this talk, I'm going just to focus on the fault injection part. So what happens when the CPU writes some data to memory? The memory controller will will compute the ECC of this data, and then it will store the ECC bits along next to the data in this, let's say, in a separate chip there on the memory. Nowadays, the memory controller and the CPU are actually on the same chip. So what happens when the CPU reads the data? The memory controller will also read these control bits. It will compute the ECC function on the data that it received. It will compare the computed ECC with the one that it expects. So, the one that expects, we'll compute it and compare it with the control bits that were stored in memory. If these 2 results are the same, then there's no error. But otherwise, if the results are different, then it means that someone or something changed the data while the data was stored in memory. And most of the times, these errors, these results are very useful to ensure reliability, availability, and serviceability for servers. So therefore, these results are somewhere saved for, let's say, later processing, as if your memory would be about on the verge of crashing, then you would get lots of errors. And then you can send someone to maybe replace the memory there. Our idea was to explicitly cause these errors, and we did so using a fault injection approach. We physically injected errors by shorting some signals on the memory bus with the custom 2 cents probe that we built with a needle. Yes, that is a syringe needle, and yeah, it was fun to build that probe at least. So the idea is that we cause this error on purpose, and then we gather this data that we can use to reverse engineer the ECC function. All of the details and all of the mathematical explanation of this is in the paper. Now, I think I covered how to get bitflips and how to reverse engineer the ECC function. Now let's look on how ECCploit actually works. First, in the first step, the attacker would recover a ECC function. He can do this offline by having a server or a target machine that is very similar to the one that he wants to target. Once he knows this ECC function, he can move to templating the memory. This is like an online phase where he avoids crashes by triggering single bit flips. He then combines these single bit flips according to the ECC function that he just fingerprinted. And it combines the single bit flips in such that they become undetectable and silent corruptions. Then we have the messaging the memory, which is just releasing the victim row with the bit flips to the operating system, such that the operating system will land some interesting data. And then finally, we run the exploit. The last two steps are exactly the same as the canonical ECC exploit. Now, so how long does it take? Does it take to template the ECC memory for Rowhammer? So on our setup, where at the beginning we had a perfect side channel, meaning that we could pinpoint which bit flipped within a row. We got 32 minutes for a page table attack, or similar results for an attack that was changing bits in some binaries. And also, there's another attack that was changing a bit in a key. This ran in 2 hours, so this was just the templating phase. Whereas the canonical exploits, where you can just directly observe the bitflip, runs almost instant. But typically, you only can guess which word actually contains a bitflip during inside the row. So this one can take like 19 hours or even 3 days on real systems. So this was our setup that had some bitflips. So it's also dependent on the memory. To conclude my talk, error correcting codes are actually just only slowing down the Rowhammer attacks. Thank you.
Any questions? Come to the center. Do we have a taker? Come on down.
Hi, Alex Solanik from Boston University. Thank you for the talk. So with ECC memory, you're sort of in a privileged position because ECC memory can detect single bit flips. You talked about the length of these attacks. Do you think that one defense could be detecting abnormalities in number of single bit corrections and sort of stopping the attack in progress before you reach the end result?
I don't have any data on this. I'm not sure how easy it would be to differentiate between normal anomaly and not. But one thing is for sure, the ECC was designed for, let's say, random bit flips. So probably if we look at the distribution of bit flips, the normal ones are distributed throughout the memory, whereas these ones that you use in the attack are very much like focused on let's say one area or one bank and something like that. So I guess there could be a way to just piggyback on these ECC errors, but I'm not really sure how much of this you can do online. So while the attack happens, so imagine that we already have a side channel. If you start processing these errors in real time, then probably the side channel will actually be even worse. So I'm not sure what is the best way if this is the best way to defend. There are other harder defenses out there that may or may not help against the Rowhammer attacks.
There's some very efficient burst error correction codes for short bursts.
Okay.
If that would help.
So yeah, I'm not sure how that actually works, but
Well, let me.
yeah.
Please use the microphone. The question or statement was, there are very efficient burst error correcting codes, and obviously in Rowhammer attack, you're creating a burst of errors. So that may be useful. But it sounds like that was heading towards an offline conversation as opposed to an online conversation.
Yeah, I guess so. Yeah.
Okay, one last question.
Guru Raj from Georgia Tech. I'm curious why there's a latency difference when there's a correction, because typically ECC, at least the SecDet codes are fairly simple to calculate, maybe a couple of cycles to correct. I wonder if the latency difference is largely due to reporting mechanism or logging mechanisms for the errors?
Yeah, sure. We have not investigated exactly, but one of the main reasons is that the errors are sometimes reported right away. So they are either logged at, let's say, the firmware level, or either even up to the operating system. So it could be that there's some machine check going on, and that is a very, let's say, brutal event for the whole CPU, and you can detect this. But even in this case, the errors were only logged at the system, let's say, at the firmware level. So I think logging plays a major role here.
All right, let's thank our speaker.